third speaker of the day is also a start of a sequence of 3 lectures. Daniele Dorigoni from Durham University, who has the title Ecalle Theory of Resurgence. So we're assuming that you will summarize all 1100 pages or something in Ecalle's 3 famous
yes,
pages.
Exactly. But I will do that in French. So
okay, that's great.
Thank you, Marcel. Let me also join Gotcha in thanking. Yeah, can you hear me? Yeah. Perfect.
Yes. Yes.
That's good. Let me also join with Gotcha in thanking the organizers for organizing this school in these circumstances. Particularly, it was a good occasion to get rid of my quarantine beard, just to look a little bit more presentable. Good. I also thought that since this was a school, I should have tried to make it more of a Blackboard style, which means that the pace is going to be a little bit slower. But I can refer to a couple of really good references. This is my particular taste. Well, I would particularly suggest the vid reference, which I'm going to be basing quite a lot of what I'm going to say. However, there's also some work. I think actually this is the first one is a paper that Gotcha also mentioned by Talaber and Pham. And also this is a shorter version actually, which is pretty nice. And I wrote also some notes, and these are the notes that Gotcha was referring to. And if you're really brave, you can actually go on Jean Ecalle's website and you can find the 3 volumes that Marcel was talking about. But apart from an introduction in English, they're in French, and my French is very broken. In first approximation is the same as Italian, but it's not quite true. And then I would also like to mention Andre's work on the return of the Porti, which I think is going to play quite a big role in what Gotcha is going to say next. Apart from this, let me just give you a brief outline of what I'm going to be talking about. So we've seen a lot of applications and already a lot of content resurgence. I'm going to be treating it a little bit more abstractly if you wish. So I'm going to first talk a little bit more about formal power series and their Borel summation, and then discuss a little bit the algebra of simple resurgent functions. And then with this, we're going to study the singularity structure of these objects and the singularity structures of their summations. And this is something that Gotcha already alluded to, the Stokes automorphism and alien derivative. And finally, I'm going to be mentioning this bridge equation that actually allows us to connect this alien calculus with standard calculus. And also talk a little bit about this large order relation that we've already seen. Good. So let me start. Well, luckily, I'm the last speaker, so we have already seen a lot of examples, so I don't need to convince you that in most of the physical quantities that we compute in perturbation theory, whenever you have, let's say, a small coupling constant g goes to 0, we have seen many examples for which you can compute a perturbative expansion. However, you will find some coefficients which are growing factorially. So what we want to see, some of the questions that we want to see is how do we actually resum this kind of object? What are the properties of the resummations of this kind of object? What kind of analytic functions we are getting out? So we are already seeing that this function in many cases are presenting non-trivial monodromies in the complex plane. They're expanded close to a bad point, in general, essential singularity. Nonetheless, they are good functions that have very interesting properties. So how do we see them? And from this object I wrote in here, I wrote specifically perturbatively. I'm not going to tell you how to do it. We're going to play the game that someone gave you some perturbative coefficients, and we try to play the game, guess the non-perturbative completion. So we're going to see how to infer non-perturbative properties out of this. Of course, this is not usually how you would go about solving a problem. You're given a differential equation, a path integral, an integral equation, and so on. But I'm going to be playing a little bit more like broader sort of point of view. And finally, something that we have already seen, these large order relations, we're going to actually understand them as a way in which the non-perturbative terms are resurgence, in the sense they are surging up from the large order behavior of the perturbative coefficient. However, before starting everything, let me switch to z equal to 1 over g. And in what I'm going to say, I'm going to be studying z much, much bigger than 1. So let me start with a little bit of setup. and specifically the Borel transform and the Borel summation. Okay, so let me first start with an object. So let me define the set of formal power series. So let us denote with Z inverse C. That's a terribly drawn C. C of Z inverse the set of formal power series at large Z. So Cn are just some complex numbers. I'm not assuming any particular convergence property. This is just a set of formal power series. And if you see, I actually removed the constant term. So this is just a technical point that we're going to remove that later. But for the moment, let me just keep it simple like this. So this is actually more than a set. This is actually an algebra. And it is actually a differentiable algebra. So it's an algebra with respect to the following product, which is what you might actually want to do. Once you have two physical observables in perturbation theory, you might wish to consider that product. And if you take their product, what you're getting out is a new formal power series with some new coefficient. How did I call them? Let me call them CK. And as a first warm-up exercise for you, show that these coefficients are nothing but the convolution of the coefficients an and bn. So this forms an algebra, and it's actually a differentiable algebra. And the derivation is just the derivative with respect to z, which satisfies standard Leibniz rule. So if you wish, for the students, this is the second part. Show that if you take the derivative of the product of two objects, psi tilde, phi tilde, then you just get the standard Leibniz rule, where this psi tilde and phi tilde are two formal power series. Of course, these are not functions, they're formal objects, so you just need to differentiate term by term. On this formal object, we have already seen multiple times that we want to consider something that actually is going to give us eventually functions. So we can define a linear operator, which I'm going to be denoting as P, which is the Borel transform. And what does this operator do? This operator maps a formal power series in Z into a new power series in T. We have used many different Borel variables. For my lectures, I'm going to be sticking with T. They're all equivalent, of course. And how does it work? You take an object of this form. Let me call it phi tilde. And we have seen many times that we're going to be giving the Borel transform. I'm going to be keeping on using the same formalism. So the tilde is going to be denoting a formal object. The same letter, in this case phi, with a hat, it's going to denote its Borel transform. And this is yet, at this stage, another formal power series in which we brutally butchered the coefficients. Took the coefficient and we divide them by n factorial. So we have seen this many a time, and the idea is that this object improves convergence. So the idea that this guy P improves the convergence properties. So for example, we have not seen many convergent functions to begin with, but suppose that we start with this formal power series, which is actually not a formal power series, it's a convergent object. So suppose that this object has finite radius of convergence. Say it converges for modulus of z less than r. Then its Borel transform by tilde of t is actually way better behaved. It's an entire function. And it grows up most exponentially. So you can estimate its modulus by some constant and some nice exponential function. With this r bigger than little r. Just to give you, well, if you want, it's another exercise, but it's more of an example. Suppose that you start with phi tilde of z, just given by a geometric series. This one gives you 1 over z minus r. So it is convergent, it has finite radius of convergence, little r. If you compute its Borel transform, I wouldn't consider even an exercise this one. Hopefully you're already going to recognize that this is nothing but the expansion of the exponential. So you see indeed that you get a better function out of the Borel transform. Of course, we want to use it to a particular set of formal power series, the one that are factorially divergent. However, as a second exercise, you can check few properties of this Borel transform. And again, let me do, as I said, as phi tilde, it's going to be an object in this algebra, and phi hat, it's going to be its Borel transform, okay? So, well, there's nothing to check, but more generally, we can take z to the minus alpha minus 1 and map it to t to the alpha over gamma alpha plus 1. So this is slightly more general. We're not going to be using it. I'm always going to assume that we start with something only with integer powers, but you can define it whenever alpha real part positive. Well, you can define it no more than that. Then the properties that I would like you to check are some properties which are extremely useful in many physical problems. So if you take the Borel transform of the derivative, this is just minus t times the Borel transform. If you take the Borel transform of z times phi tilde, this is nothing but the derivative of the Borel transform. If you rescale the variable lambda z, this you can show that is equal to lambda phi hat lambda inverse t, with lambda some complex number, well, let's say not zero, fixed. Then, if you shift the variable, is also extremely useful. You actually get e to the minus lambda t times the Borel transform. And finally, as we said before, this was an algebra with respect to a product. The Borel transform behaved kind of nicely with respect to this product. If you take this convolution product of formal power series, you get the convolution product in terms of Borel transform, which is this integral. This is why sometimes this formal power series is called the multiplicative model, and the Borel transforms are the convolutive model. So these are some of the nice properties that we can show. And of course, as we're going to see later on, we know that there is some Laplace transform in between. So it's not particularly difficult to believe that all of these properties are going to hold. So this is just the abstract version. And as I said in here, this Borel transform improves our convergence. We are going to be sticking for the rest of this lecture to a very special class of formal power series, what are called Gevrey-1 power series. So this formal power series, that minus n minus 1, is of Gevrey-1 type if these coefficients are going factorially. So if you have some alpha and some p c positive, such that these coefficients Cn are bound by alpha times n factorial. So you have various other interesting cases. So let me just remind you this little note. So suppose that you add m times n factorial. This guy goes roughly like n factorial to the m. And as Gerald mentioned, these are some interesting cases. However, by suitably redefining z, you can most of the time reconduce to just having factorial guys. So this is what I'm going to be working with for the rest of our lectures. We're going to be assuming that this formal power series is of Gevrey-1 type. Then you have the following proposition, which we have already used multiple times. The Borel transform of a Gevrey-1 type series has finite radius of convergence. Where, as I said, this phi tilde is Gevrey-1. So it's not as good as the situation as we had before. In this case, finite radius led to an entire Borel transform. But this is the next best thing, because as soon as your coefficient are factorially growing, this is a formal power series. We have seen a lot of extremely interesting resummation methods, but you always have to truncate. You cannot sum all the way to infinity. You're going to get nonsense if you just literally sum those numbers. However, the Borel transform is going to give you a new function which has finite radius of convergence. The question is, of course, how do we go back? Because remember, from this was the guy that we computed in perturbation theory, and we would like to assign a function to it. And we just constructed a new function, which is better behaved. But unfortunately, you took the coefficient and you butchered them. So how do we go back? Well, there is a Laplace transform behind. So let me define the directional Laplace transform. Along a direction theta of some function phi hat is the integral between 0 and infinity in the direction theta of e to the minus tz phi hat of t in dt. So we're picking in this t-plane our favorite direction theta, and we're going to be integrating along this line. This is a linear operator, and if phi hat of t is analytic along this ray, Then this object, you also need to put some growth condition, so it cannot really grow too fast. So let's say that it's growing at most like e to the r times the modulus of theta, so that this integral actually makes sense. Then this Laplace form gives you a function which is analytic in a half plane. And the half plane is very simple to understand. You just want this exponential factor to be an exponentially convergent factor. So you better have a real part positive for the exponent, or negative if I put the minus. So the half plane is real part of z e to the I theta bigger than r, so that this exponential suppression wins against this exponential growth. So let me draw below. Most of the time, I'm going to be calling this t plane the Borel plane, and this z plane the coupling constant plane. So in the coupling constant plane, if I integrate along that direction, I'm getting out an analytic function in this wedge of the complex plane. This is the direction theta, and this is just whatever, r over cos theta. So you see that given this direction theta, you produce an analytic function in a certain wedge of the complex plane. And the idea, so let me give the sort of physicist idea. The physicist idea is that you can write 1 as 1 over n factorial, the integral between 0 and infinity, e to the minus t, t to the n, dt. So that if you want the Borel transform along the Laplace transform along the real line of the Borel transform of minus z to the n minus 1, so the simplest example is just z minus n minus 1. So this Laplace transform is the inverse of the Borel transform. And in general, when you just don't have a monomial, what you do, you stick this one in the formal power series. So let me put a 1 in here, and instead of 1, I write this one. Of this integral. And then, of course, the commutator of the sum with the integral is 0, and you get this expression. So of course in here I put quotes because this is clearly nonsense. This was a formal object. This Laplace transform is an analytic function. However, this is the idea behind this whole process. And we have seen in many cases during this whole school that precisely works beautifully. So the key idea is that whenever we start with a formal power series, which is algebra 1, then its Borel transform, as we have just said, defines a germ of analytic function at the origin. So I'm going to be noting like this. So if you want just convergent power series around 0. And if you're interested in real coupling constant, you can decide that you take the Laplace transform in the 0 direction of the Borel transform. This is the integral between 0 and infinity, e to the minus t, z, and then this Borel transform. Of course, if we start with perturbation theory, whichever function I'm giving you should be asymptotic to the perturbation theory you started with. And indeed, this object is asymptotic to the perturbative expansion that we started with. But this is a function, okay? So let me stress again, this is a function, and this was a formal object. We have seen a lot of resummation ways to make sense of the optimal truncation plus exponential bound. However, in my definition of phi tilde, I was summing over all of the coefficients. So clearly it was only a formal object. So morally, this Laplace transform, you can think it of as the inverse of the Borel transform. So as a summary of these ideas, a pictorial summary if you want, we start with a formal power series. Of Gevrey-1 type. And from here, we apply the Borel transform, and we get to a germ of analytic function at the origin. So in here, you really get a function with a finite radius of convergence. From here, we apply the Laplace transform. We took L0 of the Borel transform of phi tilde. This gives us a function of z, which is the integral between 0 and infinity, e to the minus tz times this Borel transform. Is analytic for real part of z bigger than r in this case. Well, remember, r was some exponential growth of this phi hat. What's the connection with the formal series we started with? If you just do an asymptotic expansion near infinity, the asymptotic expansion of this function gives you this formal power series. So this kind of closes the circle. Of course, this is one possible resummation. I picked, sorry, the 0 was down below. I picked a particular direction of resummation. I decided to integrate along the real line. But nothing is particularly special about the real line in this case. So we can define what is called a directional Borel resummation. Of, again, phi tilde, Gevrey-1. And let me denote it as, I think I'm using the same convention as Gotcha, as theta of this formal object in here has the Laplace transform in the direction theta of the Borel transform of phi tilde. So this is nothing but the integral between 0 and infinity in the direction theta of e to the minus tz and the Borel transform of phi tilde, which is a function of t. If this integral exists, and that's the key point, if the integral exists, it defines an analytic function in a certain wedge. In the wedge, real part of z e to the I theta bigger than, again, this r growth. So this is the key point of doing this Borel resummation. And again, let me stress it that this object, of course, is asymptotic to the formal power series we started with. So again, the name of the game is I gave you a formal power series. You want to give me a function, an analytic function somewhere, whose asymptotic expansion is the series I gave you. Well, any object of this form will do the trick. So to give you another exercise, we have seen it more than once in this series of lectures, but as the Latin used to say, repetita iuvant. So let's consider once again an Euler type of equation, phi prime of z minus phi of z equal to minus 1 over z. And I think we have already solved this probably yesterday. My short-term memory is gone. The first thing is to find a formal power series solution to this problem. Let me call it phi tilde, which vanishes at infinity. Then from here, we can compute this particular summation, the lateral, the directional Borel summation along the real line of this object. And this defines a function. You can use Mathematica to compute this integral. Then you can show that this function now solves the differential equation. So you gave me something which is formal, and using this whole procedure, you actually produce a function. And finally, you can use this phi tilde to give a possible meaning to this series that it appeared in Euler de Siribus Divergentibus, as I forgot now who mentioned that, I'm sorry. I think, I want to say either Adri or Chris. I remember the picture of the first page of this paper in Latin, so I do apologize. Good. Perfect. So I should stress that this method in here works really well for this kind of algebra 1 series. In some cases, whenever you're dealing with assigning numbers to these objects, you might want to do something else. So of course, in here, we are talking about formal power series. So we're going to be interested in the analytic continuation of formal power series. But I'm sure every one of you have seen object of these forms. Well, the sum of the integers, which everyone knows it's minus 1 over 12, but like this is a different analytic continuation. So if you try to apply Borel transform in here, you're going to get infinity to this sum. So you don't even need to do, these are not factorially growing coefficient. But of course, this is intended as a Dirichlet series. So analytic continuation of Dirichlet series is a different story. Okay, so before moving to the next topic, let me have a look. I cannot see, unfortunately, the chat from here. Oh, no, I can. Perfect. There is no question so far. I do apologize. The start is fairly slow, but I thought we were all better to get on the same page. Good. So at this point, we want to understand a little bit better what kind of functions we are dealing with. So we want to understand algebra of simple resurgent functions. So the key point is we want to understand the analytic properties of this type of object, or equivalently, the Borel transform. So the idea is that if your Borel transform has no singularity in a certain sector, in the sector, say, argument of t between θ2 and θ1. So let me make a little drawing in here. So this is the t-plane, and I've picked two directions which are particularly lucky. Between these two directions, this Borel transform has no singularities. Then, modulo some convergence at infinity, if you consider the two lateral resummation, sorry, the two directional resummation, S of theta 1 and S of theta 2, these are in principle two different analytic functions. I'm integrating over different contours. However, if theta 1 and theta 2 in this sector, the Borel transform has no singularities, these two objects will coincide on the common domain of analyticity. So you can think them as one being the analytic continuation of the other. So let me draw now the coupling constant plane. And let me also assume that the Borel transform is not growing exponentially fast. So I'm drawing all the wedges going to the origin. So S of theta 1, it's analytic in this wedge. So this is theta 1. And this is the domain of analyticity of S of theta 1. And now, since I have this one, we can draw another color. Theta 2 is this one. S of theta 2 is analytic in this wedge. In this shaded region, which is common to both, we have that S of theta 1 coincide with S of theta 2. So they must be analytic continuation of one another. So you see that in this lucky scenario, you can actually extend the domain of analyticity by taking the union of the two. So the full domain of analyticity can be extended to this bigger wedge. However, the key point is singularities. The Borel transform in general has singularities. So this case, you can, well, we wish that there weren't too many singularities. So this poses a restriction on type of function that we want to consider. So the first thing that we want to put, we do not wish too many singularities. So let me give you a definition. We say that this germ of analytic function at the origin is endlessly continuable. Morally speaking, is if you can pick at random a direction and integrate in that direction. If, so it's endlessly continuable on C. If for all r bigger than 0, you fix your favorite radius, you check how many singularities you have within that radius. There are a finite number. There is a finite set, gamma r, which depends, of course, on the function, depends on C, of what are called accessible singularities. What it means is that this function phi hat can be analytically continued in all possible directions while avoiding these singularities. Long all paths gamma emanating from the origin with length less than r and avoiding this set of singularities. Of course, not all functions have these properties. In particular, we want functions. So the idea is that you want functions without natural domains, natural boundaries of analyticity. You might think that, and actually there are, but you might think that there are a condensation somehow of analyticities, or of non-analyticity, sorry, that somehow bounds your domain. This is a situation which we do not want. They're interesting on their own. So just to give you an example of something like this, but they are different objects. I can consider L of Q of this form. This is called a Lambert series. Q to the n divided by 1 minus Q to the n. With Q a complex number, and the modulus of Q is less than 1. So we are within the unit circle, but then you see in here that something really strange is going on. Thanks to this denominator, I have a singularity. So L of Q is singular whenever Q to the n is equal to 1, with n an integer. But this is telling you that at all rational root of unity, you have a singularity. But unfortunately, the rational points are dense on the unit circle, so this object actually has a domain of analyticity which is bounded by the unit circle. So if you go to each rational root of unity, this object is actually singular. However, there is a way to study this object, this type of objects, but is not what I'm really talking about in these lectures. We want to have objects which do not have natural boundaries of analyticities. I want to be able to integrate along possibly well, for sure along an infinite number of directions, or let me put it the other way, I do not want to worry about more than a finite set or a countable set of singular directions. So we are not going to be looking at objects of this form. And then the other thing that we want to discuss a little bit about is what type of singularities. And I'm going to keep it simple. We don't need to do it. Well, we have seen that there's a lot of different types of singularities. We have seen a lot of examples with log singularity, branch cut singularities, and so on. Let me just keep it to the simplest example of what are called simple singularities. So let's say that phi is a holomorphic function in a disk. We say that has simple singularities. At omega, which belong to the closure of the disk, if there exists alpha complex number phi hat of t, regular of t, germ of analytic functions at the origin. So these are analytic functions around t equal to 0, such that our function phi hat, when I approach this singular point omega, behaves in a very simple way. It has a pole and it has a branch cut of logarithmic type, multiplied by this function capital phi. Everything else is regular when t tends to omega. So you see here, I'm not giving you the most general version. Of course, in general, you should never go for pole or log. You should just go for like random branch cut. However, let us just stick for simplicity to this type of singularities. So as I said, this reg is the regular part. This alpha is the residue at the pole. And this phi hat, this function that multiplies the logarithmic branch cut, is what is called the minor. Good. The key idea that we are going to be using, well, at this point next time, is that this object in here, this type of singularities, are somehow closed under the natural product that we were discussing about. These simple singularities are stable under the convolution. It doesn't mean that you don't generate more singularities. It just means that if you start with poles and logs, you're going to stay in the realm of poles and logs. It just simplifies a little bit the story. And let me conclude today's lecture with an exercise. I believe this is exercise number 4. Let us assume that phi tilde takes this form. And factorial z omega the minus n minus 1. So perhaps the easiest example of a Gevrey-1 series. Then, okay, the first thing, but this is not even an exercise, compute the Borel transform. And you will find that, surprise, surprise, is of this type in here. And actually, I chose it just by choosing purely factorial coefficients. The only thing you have is a pole. And the location of the pole, as we have seen many times, is given by the, whatever number is multiplying your small parameter, on this case, large parameter z. Then, take the following. Take another formal power series, which is just Z inverse. Well, not really an exercise again. You can compute the Borel transform, and you're going to find 1. At this point, let me ask you this. What are the singularities of 1 convoluted with 5? This is the convolution of this object in here. And you can compute it in 2 different ways. You can either take the Cauchy product of these 2 objects and then take the Borel transform and see the singularities, or you can directly take the convolution product of these 2 objects. And what I want you to appreciate is what is going to happen to the singularities when you take this sort of convolution. And the second and final part is, okay, let us take now 2 of these guys. Let me take phi 1, which has a pole at omega 1, and phi 2, which has a pole at omega 2. What are the singularities of phi 1 convoluted with phi 2? You will see that something new happens in this case. Excellent. So let me stop in here for today, so we can see if there are questions, and then we can move to the tutorials.
Thank you very much. Yes, there was one question in the chat.
Perfect.
At some point you said that the Dirichlet series cannot be done using Borel summation. Can you explain that again?
Good. Well, yeah. So what I wanted to say is that so in the case of, well, that was the case that I was giving you before, right? So, okay, the way you do this object in here is you define another type of analytic continuation. So you do analytic continuation in this parameter S. But you see that this is not a formal power series, right? This is a what is called a Dirichlet series. So usually a Dirichlet series, you start with some coefficient n to the S, and you define, and you study the analytic properties with this parameter S. But this is clearly not a formal power series. What I was saying is that you could try to stick a z to the minus n minus 1. So this would define one of these phi tilde. And you would think that Borel transform is going to work beautifully, because you see these coefficients are not growing factorial, they're growing linearly. However, that if you wish, it's another exercise. Try to use this one. You try to take the Borel transform at 1. Sorry, you take the Borel resummation at 1. You would like to say that this is morally the same sum in which I put 1 in here. Well, you will find that this object is not minus 1 over 12. It's actually infinity. So it doesn't work in the same way. The reason is that we want to consider a different type of analytic continuation. Here is not an analytic continuation of this type, it's an analytic continuation of this type. I hope this clarifies. I think Daniel is also a question.
Yeah.
The endless continuation was defined in the Borel plane. Is there a way to say if a given formal series Gevrey-1, say, in the Z plane would result in an non-endless continuable Borel transform without actually taking the Borel transform explicitly? I guess I'm asking, can we spot bad formal perturbative series for which Borel plus Laplace won't succeed? That's a good question. On the spot, I don't know. I'm sure you can come up with some very, very bad example in which you're getting more and more poles. So there is this lacunary function, which actually has a similar property, and it's actually a power series. But I'm not sure if just by staring at the coefficients, you can actually say that. I'm sure that you can come up with some very, very weird example, which is not going to work. I should also say the object that I wrote before, you can actually study that via power series, but you need to work a little bit harder, because this object in here, you can actually expand the denominator. And so just by expanding this one, we get something of this form. And this is very nice because you can rewrite it in this particular way. So you just put what is called a divisor sigma. So you see in here, just fix on this power. Whenever this number n times n is constant, you just need to count. And this is exactly the sum, this sum in here, what is called a divisor sigma. You're literally counting the number of divisors of this power in here. For any pair n and m, this is going to give you an object of this form. And at this point, what you do, you replace this object with e to the minus, well, let me keep it simple, n times y. And you study the power series expansion of this guy when y goes to 0. So when y goes to 0, q tends to 1. And actually what you can do, well, let me put an I then. And actually you can check whenever y tends to some rational number. This is when q tends to 1. And this object in here, you can actually study it. And although you have a lot of singularities in the q plane condensing on the circle, from the point of view of the y plane, which is just the upper half plane, in here everything goes well. The only problem is when you reach this part in here. But the coefficients are perfectly fine actually. From here you can get, by doing some other trick, you can actually get just some Gevrey-1 series. But in general, if you just give me some random Gevrey-1 series, I don't know how to spot if it's, I'm sure you can come up with some very good example.
And this one is even better than Gevrey-1, right? The coefficients grow very slowly. So
yes,
fast growth is not a problem.
Yeah. There was also something in the chat. Oh, no, that was just the link.
That's the link, yeah.
Perfect.
Okay, so Thank you very much, Daniele, for this very nice first
Thank
lecture.
you.
Looking forward to the rest. So to all the participants, indeed, you can find in chat some remarks about where the tutorial will be. The link is there, so you can just click it if you don't have it anymore. You can also find it back in the welcome back PDF. So for this session, that's all. The other session is another Zoom meeting. So let me thank Daniele again, and let me thank all three speakers of today again for a very nice session. I will see you all in the lectures tomorrow.